Hey there, this is Max, and this is the FD Poison Challenge Solution Guide. Now, I'm going to be upfront with this. I'm probably going to make some mistakes going through the code, writing this exploit. Writing exploits live is hard, and even for me, writing binary exploitation-based exploits takes time and thought, and looking up how to do random things in Python. So, be patient, but I think it's good to see how I debug stuff when things don't work. So as normal, I'm first going to go through a more graphical solution to this challenge, and then I'll show you the bug in the source code, and then we'll write the actual exploit in component tools. I'm going to I'm going to turn off the camera for a sec while I go through the slides. So first, when you review the binary, knowing your data structures is important. So here we have a kid struct, we don't have know what operations are available, and it's just a nice shell for us. That's not the case in real world things, but for CTFs it's fairly common. So just knowing your possibilities is good. Now, this is the order of operations I would take for this. First, you need to find the use after free vulnerability. After that, you need to get a leak from the heap address. You can then use the UEF to do the FD poisoning technique, set that over the top of a function pointer, and then pop a shell. So this is a pretty straightforward use after free vulnerability. The kid can be freed and accessed at the same time. So if you use a UAF, or if you create a kid and then free the kid, and then you can print or edit, and at that point you have a use after free, and the whole thing's busted. It's not good. I'll show you why that's the case in a moment, though. So, in order to get the information link, there's a couple things you can do depending on what version you're using. By default, this is using glibc 2.26. I think there is a Mangling version of this. And the Mangling version actually has support for the key one here, but you don't need to do that in this case. So the age is going to line up directly with the FD pointer. So if we just read the age, the age has been corrupted, and we can read that as an FD pointer, and that gives us a nice heap leak. For the actual technique, now we have to think, we have the information leak, so we know where to specify the pointer at. But where's an actually nice place to put it at? The best place to put it is the function pointer that is on top of the kid struct. So based upon the information link we've gotten, we can now go back to the heap base, and once we're at the base, we then can figure out how many bytes is going to be to that function pointer, and then we can specify that to be what we want to use. So with that, we can specify the FD over the top of a function pointer. So now when we allocate, or we have this, we have pointer one, or chunk 1 pointing to a function pointer. So we have to allocate once, we allocate again, and now we're over the top of the function pointer with our kid. Finally, we just call print with the age value that we specified, and the age value should be the pointer to the win function, and we pop a shell. So this overlapping nature causes this really bad issue. You can do this with both the age and the name, but it's easier to do with the age because you don't need to pack stuff. So to recap, we have a use after free vulnerability where we need to leak the heap address via the UAF on the FD pointer. Then we need to use the UAF on the FD pointer again to edit the FD to sit over the top of a function pointer. And finally, we need to allocate the heap chunk over the top of that function pointer to specify the win function. Cool. So that's how this exploit works. And now we're going to look into why the vulnerability exists in the code in the first place. So there's a global structure for keeping track of the kid called allKids. And we can see within create kid we're returning a pointer. And it is then specifying all kids within all kids counter within this. Now, the actual issue comes from when we free the kid. In order to prevent use after free vulnerabilities, you want to do something like all kids of index, or second option in this case, equals null. So if it's null, then you'd also want to have it check that so you don't have null pointer dereference, but this prevents the actual exploitation of it. But that's not there. So the issue is that all kids still has a pointer to something that we've already freed. So in reality, the counter just goes up and doesn't really consider the issue of freeing in the first place. And if we go to the terminal here and we access this, we can actually see this pretty easily. So the start.py function actually creates a kid at the very beginning, so we already have a kid. So if we go back up, we can do print, and we can see that the kid was actually printed up here. Alright, so now I'm going to call free on the kid. And now if we go in here and we look at bins, this is there. We can also do p all kids of 0. And that pointer is still there when it shouldn't be because we've already freed it. So if we go up here and we try to do view kid at index 0, you're going to get some kind of weird values. In particular, the age is set to 0, even though that's not what we set to the age in the first place. The reason the kid is set to 0, though, for the age, is because the FD pointer of something that has only been freed that one time is, of course, going to be null. Because it's the end of the linked list, the end of a singly linked list is always going to be null. I don't like this. Poop. Okay, there we go. Now my tmux session is not freaking out anymore. Cool. So at this point, we now know that we can view a kid. And we can view them while a use after free is actually happening. So what can we actually do here? Well, we can use the use after free to get the heap leak. But of course, we need to create more than one kid so that we actually have an item that we were able to leak. So I'm going to have 2 kids, and all I don't have to do this, when I write exploits, I like to have different values just so I know what chunk I'm looking at. So I do Maxwell with hex 20 and Maxwell 2 with hex 21, just make the tracking of my stuff easier. So now we need to do free kid, and this is going to be index 0 and index 1. So I'm just going to do free index 1 and free index 0 just so I operate on these in the future. So at this point, the linked list is going to look like this. It's going to be 0, 1 in the hex 30 tcache bin. So if we do a print of view kid of index 0, then we'll actually get the values we want to see here. So if we go up above, and we can see that we have indeed printed Maxwell, and this is an integer, and I made it nice for you guys to just print in hex. So if we keep track of this value and then go down here, we look at the bins, we can indeed see this. So this is going to be the kid1 pointer that we found. And if we print all kids again, like we did a moment ago, oh, that is not what I meant to do. Too many references, cool. So we can see that these pointers are exactly the same. So we're using the freed FD on kid 0 to look at kid 1's pointer. And you'll notice that we have this 290 here. If we look at the heap, we can then normalize it. So when you have these programs that are absolute like this, where it's completely deterministic with the allocations, it's pretty easy to just go back to the beginning of it. So this first chunk here is going to have the 0, 0, and the 8, 7 is going to be the prefix of that. So we know that with this leak at 290, we need to subtract hex 290 to get to the beginning of the heap. If you're doing something that doesn't have these deterministic allocations, then you need to do them relative to each other. And this requires a little bit more grooming, and in a program like this, it's pretty easy because they're going to be consistent. But if you're looking at a real world target, it does become more complicated, and you have to be a little bit smarter about it. But in this case, I'm just going to subtract hex 90 from our pointer. So we have name and age here. And we actually don't really need the name in this case. If you did this leak in a different way, in a different version, you may want to use that instead though. So I think I want to do age of 16. Do heap leak. We want to do 16 because we're taking a string and converting it to an integer, but it has the 0x in the beginning of it, which means that it's going to be hexadecimal when it gets received. There is a space at the beginning of this, and there is a new line at the end of it. So I'm just gonna do some string parsing there as well. And I didn't print that. So I'm also going to do a print of this. I'm going to remove the interactive portion because I'm lazy. Alright. Okay. Yeah, that's great. So we can see here that we have the leak of that 290 at the beginning. So now, in order to get to the heap base, we are going to subtract the hex 90. So heap leak minus 290. Cool. So that gives us the heap pointer and where we can start from. Awesome. So at this point, we've used the use after free to leak the address. Now we need to use the use after free to edit the FD pointer. But where do we actually want to edit the FD pointer at? As we said in the slides before, see if I can pull this up in the slides. We want to specify, we want to overlap the fake chunk's age with a different kid's function pointer. This way we can use the age to write the function pointer on that kid. So I'm going to choose to do that over the kid's function pointer for kid 0. So I'm going to turn the interactive back on. And then we're going to figure out what address we actually want to point this to. So like before, we can do the print of the kids. And I'm going to do this on index 0. Oh, whoops, I need to do the continue, and then I can do that. Cool. So here we can see the kid, but what I care about is the reference to this location. So I'm going to do this. And this gives us the absolute address of that we want. So this is going to be the address to the function pointer. And if we do that, it actually tells us this is the beginning of the function print older kid. And the address is hex 80. So of the data we actually want to overwrite. So again, we could have just done like a minus hex 10 on the leak, but I like going to the base and then going forwards because it's a little bit more universal. And if was more complicated stuff to do, it's nice to just be able to add instead of arbitrarily subtract things. That's just a preference, but it's up to you how you do that. So now we're going to specify func pointer address, and it's going to be heap base plus hex 280. So now we need to actually edit the pointer, and we know where we need to edit the FD pointer to point to that location. If we look at the bins, we can see that we have a 260 and a 290, which is where we got the leak from before. So we're going to edit this 260 to point somewhere else. And just to showcase this, we can do this in the CLI pretty easily. If we do edit kid, index 0, we don't care about the name, and we can change this to be 16. Now, if we look at the bins, we can see that we actually have edited this. It starts at 260 and then it goes to 10. You're wondering, why are we editing the hex 90 here and not the hex 60? Well, the Tcache itself has a data structure that has the head to the list. So the FD pointer we're overriding is effectively the second item in the list. But after we allocate a chunk, it will take this as the pointer next time. For instance, if we create a kid and specify their age, and then we go back down, and now if you look at the bins, you'll notice that this hex 10 is there. And if we do the print of 2, because that was the second one we allocated, we can see that the 260 is done again. Now if we do this one more time and we try to create a kid, the program seg faults. And it seg faults because it's trying to use a chunk that should not be used, clearly. Okay, that's fine. So now we have a better idea of how this exploit actually works. We just cause this to crash by a bad FD pointer. So hopefully we can allocate this correctly now. So we're going to create kid Maxwell 3 and hex 22. But before we do that, we need to do the edit kid with index 0, and the name is next. And then the age is going to be the function pointer, and that's an integer, so that's fine. So just to show what this looks like, we're going to run this through, and then if we do print, or if we use bins, we can see that this now points to the function print older kid. This hex 280 is the value we specified. So if we do 2 more allocations, we'll actually go over the top of it. So we have 1 allocation, and this is index 2, and this is going to use chunk 0 that we initially used. We're going to create kid again, and this is the malicious chunk this time that we specified. So again, we don't care about this. Oh no, I messed this up. Wait, no, the function, yeah, that's good. So the function pointer address is the FD pointer, that's good. And then when we create this kid, the key here is we need the win function. So I'm just going to specify a bunch of 1s to begin with. But this is going to use the func pointer address as our as the chunk now. I'll show you what I mean. So we're going to continue. And now we don't have anything in the bins because it's empty. But if we look at print kids of 0 and we look at the print info here, it looks kind of different now. and this is going to be the Maxwell 4. So wait, so oh no, it would be index 3. It would be index 3. That's fine. So we do continue, and it's index 3 because it's item 4, so that's fine. I just got confused on. I ran off by one error in my head. So now the print info is going to be fine for 3, but it's been allocated. But the key is where it's allocated. So if we look at print all kids of 0, the print info should be kind of strange looking here. That's not a real pointer. So we've given it a value that's invalid. I'm guessing that that is just a bunch of 1s if we looked at it, but not. Copy that, and then I do this all the time. I just go and like look in Python real fast, like with a print in value. That is all 1s, so we're able to corrupt that. But just to drive the point home further, if we do, I need to continue. If we actually get the address of this print info here, notice that that's the 280. And then if we look at print all kids of 3, these are the same pointers. So that really demonstrates that we were able to use the FD poisoning technique to put a chunk incorrectly into the T-cache. So the final portion to this is we now need a function to actually call. Because if we go up here and we call viewKid, the program crashes because it doesn't know what to access. It's accessing a pointer that doesn't exist. So this is where we just need to find the address of the when function. Oh, come on. There we go. So we have the address of the when function, and we're going to go write that. Instead of this 111 value here. So now we're going to do start.py. We're going to do continue. And then we do viewKid, and this on index 0, and this triggers the shell. So if I do who am I, we can see that this does run, and we can actually see what's going on here. Awesome. So we just wrote the entire exploit in one sitting. I'm shocked that worked as well as it did. I only had a couple brain farts. So we can look at this one more time just to recap what's going on here. So we have a use after free on the kid structure. We can allocate a kid, free the kid, and then either print for a leak or edit it for the FD poisoning technique. After that, in order to get the leak, we're overlapping the age and FD together. And because the FD is part of the age and it's insecure, we can easily see it. After that, we want to specify the fake FD and the FD poisoning technique to sit over the top of the function pointer on another kid. And of course, you could use something like the God table or something like that, but just for simplicity, I didn't want to do that. After that, we have a function pointer in the FD list. So we allocate once, the function pointer is at the beginning of the list, we allocate one more time, and we can then overwrite the function pointer on one of the kid indexes. We write the age and it does that. And then finally, we pop a shell. Winner, winner, chicken dinner. Cool. So if you got through this all the way, congratulations. That is really awesome. If you didn't, I still think there's a lot of value in seeing this, learning how pwnable works, and seeing how somebody like me does go through about these exploits. That's probably the last part of this module. This may be somewhere else. It may not be right after FD Poison, but if it isn't or it is, doesn't really matter. Hope you got a lot out of it. Thanks for watching and going through it.